So now that we've pinned down the theory with complete proofs, let's do another example, this time a 3 by 3 one. So we're going to look at the matrix. A is going to be the matrix 1, -3, 3, 3, -5, 3, 6, -6, 4. This is going to be the matrix A. It's a 3 by 3 matrix, and it has a corresponding linear map. T of V equals AV, right? The map goes from where to where?
From V to alpha.
The map T corresponding to this matrix, defined by T of V equals AV. What are its domain and range?
Matrix 3 by 3.
No. This matrix has a corresponding linear map, defined by T of V equals this matrix times V. Right? That's how we get a map from a matrix. What are the domain and range of T? T goes from what V to what V? From what vector space to what vector space?
I think we need to know.
You don't need to know anything.
3 tuples to
3 tuples, okay, over what field? F, okay, but it's okay.
R.
Okay, usually R. Right, it could be C3 or Q3 or whatnot. Okay, so T goes from R3 to R3. Everybody good? You understood all those proofs in the previous lesson, and this is still an obstacle?
No, the question, we weren't clear on the question.
Right. It's my fault. I take the blame. The question wasn't good. Okay, clear? Everybody with me now? Okay. We want to find the eigenvalues and eigenvectors. That's the goal. How do we do it? We're not going to decipher it again. We're just going to use the theorem. We worked hard for the theorem. Now we can use it. Here it is. The eigenvalues are the roots of this polynomial, t minus alpha I. I'm going to write what t, or a minus alpha I if t is given by a matrix. I'm going to write a minus alpha I, find its determinant. It's going to be a polynomial in alpha of degree 3, right? Because it's a 3 by 3 and there are alphas across the diagonal. There are going to be 3 of them. I'm going to find the roots. For each of the roots, I'm going to plug it in here and find the kernel of the system a minus alpha I, which is the same as saying solve the homogeneous system a minus alpha I. Okay? That's what we're going to do. That's it. Everybody good? Okay, let's get going. So the first thing, find the characteristic polynomial. What is the characteristic polynomial? It's a minus alpha I determinant. That's what we want to find. So here it is. 1 minus alpha. I'm subtracting alpha I. Alpha I is just a matrix that has alphas across the diagonal and 0 elsewhere. I'm subtracting it from this matrix. So it's 1 minus alpha minus 3, 3, 3, negative 5 minus alpha, 3, 6, negative 6, 4 minus alpha. That's it. That's the characteristic polynomial. What you're looking at is a polynomial in the variable alpha. Do you agree? The determinant of this thing with parameter alpha is a polynomial in alpha. Okay? How do we find the determinant? Well, we know that we can either calculate it according to the algorithm, choose a row or a column and use it to evaluate the determinant. Or we can do some preliminary steps that preserve determinants, or maybe change them up to a sign and so on. Okay, so that's what I'm going to do. So the first step I'm going to take, I'm going to add the second column to the first column in order to get rid of one of the 6's here. Okay, so add the second column. Let's use R for rows, just like we did, and C's for columns. Add C2 to C1. So what do I get? Let's write it here. What do I get? I get 1 minus alpha minus 3, so I get minus 2 minus alpha. 3 minus 5 minus alpha, so I get minus 2 minus alpha here as well. Good, I like seeing things like that. And 6 minus 6, I get a 0. That's what I wanted originally. Okay? And then the rest are untouched. Negative 3, negative 5 minus alpha, negative 6, 3, 3, 4 minus alpha. Good? Next, I'm going to pull out a negative 2 minus alpha from the first column. When I pull a scalar out of a determinant, okay, when I multiply a row by a scalar, it gets pulled out of the determinant. Just the one row, not like a matrix. Okay, so this equals minus 2 plus alpha, and then I have the same determinant, but now these are ones. So I have 1, 1, 0, and the rest are unchanged. Negative 3 here, negative 5 minus alpha here, 3, negative 6, and 4 minus alpha. Good? Next, I'm going to subtract this row from this row. Subtracting one row from another preserves the determinant. And notice that when you're working on determinants, you can do interchangeably operations on columns, operations on rows. That's fine. We're following the rules of working with determinants. It's not the same as row operations for reaching an echelon form. It's completely different. Okay? So I'm going to subtract R2 from R1. Let's write that. Subtract, which one? R1 from R2, right? R1 from R2. Okay? And I'm going to write it on the next board. Tell me if you agree. So what we get is, wait, there's this 2 plus alpha out there that we can't just ignore. So minus 2 plus alpha, and then there's the determinant, and what we get is 1, 0, 0, negative 3, negative 2 minus alpha, negative 6, and 3, 0, 4 minus alpha. Tell me if I did it correctly. Okay. And now I'm just going to evaluate the determinant using the first column. Okay, so the determinant is going to be, there's going to be this negative 2 plus alpha here, not touching that, and then there's going to be 1 times this minor, and the other two are gone because it's zeros. So there's this 1, which I'm not writing, times the minor, negative 2 minus alpha, 0, negative 6, 4 minus alpha, right? And now this is this determinant I'm just going to calculate. So it's this times this minus 0 times negative 6. So I'm basically done. There's minus 2 plus alpha and another one from here times 4 minus alpha. So the minuses cancel. I have 2 plus alpha squared times 4 minus alpha. That's my characteristic polynomial. It's a polynomial in the variable alpha, and by doing it the way I did, I even obtained it already factored. And that's a good thing, because factoring polynomials of degree 3 and higher is non-trivial. Okay, and we don't even know precisely how to do it unless they're special. So it's always good to manage to somehow get them that way to start with. Okay, so this is P of alpha. This is the characteristic polynomial of the map T defined by that 3 by 3 matrix. Good? What do we need to find?
Roots.
Its roots. But it's factored. What are the roots?
12 and negative 2.
Right. So the eigenvalues, that's it. The eigenvalues, let's not give them names. So the eigenvalues are alpha equals negative 2 and alpha equals 4. Those are the roots of this characteristic polynomial. Those are the eigenvalues. That was part one of the theorem. Okay? Now there's a difference between this alpha and this alpha. This one, 4, appears once as a root, whereas this one, -2, appears twice in some sense. It's a double root. Okay? And that's important. We're going to discuss it in the next clip more precisely, but it's an important observation, and it has a name. Okay? There's terminology that goes along. What we say is that -2 is the root of multiplicity 2. Okay? Whereas 4 is the root of multiplicity 1. Okay? But there's another notion that's going to carry the same name, multiplicity, and they have different meanings. So this is called algebraic multiplicity. Okay? So alpha equals -2 has algebraic multiplicity algebraic multiplicity 1, whereas alpha equals 4 has algebraic multiplicity 2.
Is it the other way around?
It is the other way around. I'm stupid, sorry. Has algebraic multiplicity 2, and this has algebraic multiplicity 1. Good? Everybody? Okay. So that's it. We're done with the eigenvalues. And you can see that it wasn't very long, right? We knew exactly where to start. We just right away wrote down what the determinant that we need to calculate is, and that's it. Okay. Now we need to find the eigenvectors. The eigenvectors, for each of these alphas separately, we're going to take them and plug them in where? To A minus alpha I, and solve the system that we obtain. Okay, so en route to the next clean board, I'm passing again along the theorem. If alpha is an eigenvalue, I need to find the kernel of A minus alpha I, or T minus alpha I. Good? So let's start with alpha equals -2. That was our first eigenvalue. So what we need is to take A minus alpha I. A minus alpha I is what in this case? So I have A on this page. You can check that I'm copying it correctly from the previous board. So it's A minus -2 along the diagonal. Okay? So it's 1 minus -2, and then -3, 3. And then 3, -5 minus -2, and then 3, and then 6, -6, and 4 minus -2. This is A minus alpha I, where alpha is -2. Good? And then we can, of course, calculate the numbers. So what do we get? We get 3, -3, 3, 3, -3, 3, and 6, -6, 6. This is A minus alpha I, right? Good? And it's concrete. Once alpha is concrete, this is a concrete matrix. Okay? So what do we want? We're looking for the eigenvectors are the kernel of this times v equals 0, right? So eigenvectors, the eigenvectors corresponding to this alpha solve 3, -3, 3, 3, -3, 3, 6, -6, 6 times x, y, z equals 0. Those are the eigenvectors. That's the kernel. It's the null space of this matrix. Do you agree? Right? So this is a system of equations, a homogeneous one. We're looking for solutions, right? But in this case, for alpha equals -2, what we got is a matrix where all 3 rows are in fact multiples of the first row, right? So in fact, the solution is eigenvectors solve this. Not all solutions are eigenvectors, right? Which solutions to this are not eigenvectors? Are all the solutions to this system eigenvectors? Right, the trivial solution is not. Right? Because eigenvectors by definition are non-zero. So which are they? So 3x, the solutions are 3x minus 3y plus 3z equals 0. Or another way of saying it is x minus y plus z equals 0. Or another way of saying it is z equals y minus x. Those are the solutions. So a general solution, so general, so eigenvectors of alpha equals negative 2 are vectors of the form x can be whatever you want, y can be whatever you want, but then z is y minus x, right? You have 2 degrees of freedom. The rank of the matrix is 1, so the null space, right? The rank nullity theorem, the rank of the matrix is 1, so the null space is of dimension 2. So you have 2 degrees of freedom, right? Everybody with me? Is the terminology sitting well? Okay, 2 degrees of freedom, and now let's choose 2 of them, and a natural choice would be 1 and 0 and 0 and 1. Okay, to make them as simple as possible. So choose v1 corresponding to alpha equals negative 2. We're going to choose 1, 0, and then the z is going to be 0 minus 1. So we're going to get negative 1. And v2, choose 0, 1. So we're going to get 1 minus 0. So we're going to get 1. So these are the 2 eigenvectors corresponding to the 2 linearly independent eigenvectors corresponding to alpha equals negative 2. We can write infinitely many more, but they're just going to be linear combinations of these guys. Do you agree? Good? Okay. Now we have to do the same thing for alpha equals 4, for the other eigen value. Okay, so let's do that. So for alpha equals 4, I'm debating with myself, what do I want to erase? Let's erase here. So
That's a quick question.
sure, even a slow question.
The multiplicity basically gives me the amount of vectors that I'll get from that root.
Okay, so we mentioned that alpha equals negative 2 has algebraic multiplicity 2. And we found here that alpha equals negative 2 has 2 linearly independent corresponding vectors. This is going to be called, this phenomena is going to be called, that alpha equals negative 2 has geometric multiplicity 2. Okay? The number of linearly independent vectors corresponding to a eigenvalue is called the geometric multiplicity of that vector. Let's write it. Alpha equals negative 2 has geometric multiplicity 2. It has 2 linearly independent eigenvectors that correspond to it. Okay? I'm going to define these things formally in the next clip, and let's just give a giant spoiler. The theorem is going to be that the matrix is diagonalizable if and only if for every eigenvalue, its algebraic multiplicity and its geometric multiplicity coincide. Okay? So if it appears twice in the characteristic polynomial, it has to contribute 2 vectors to the basis. If it appears 7 times, it has to contribute 7 vectors, and that's not always going to be the case. Sometimes you'll see an eigenvalue appearing 3 times, and its null space is going to be of dimension 2. It doesn't contribute enough vectors to the basis, and then in that case, the map or the matrix is going to be non-diagonalizable. Okay? But we're going to say all that ordered in an orderly way in the next, okay, so we're just kind of observing these things in this example. We'll say them formally later. Good? Okay. So back to alpha equals 4. Back to alpha equals 4. We want to do the same thing. So a minus alpha I in this case, a minus alpha I, is again 1 minus 4, negative 3, 3, 3, negative 5 minus 4, 3, and 6, negative 6, 4 minus 4, which is the matrix negative 3, 3, 3, 3, negative 9, 3, and 6, negative 6, 0. That's a minus alpha I when alpha is 4. And again, we want to solve the system. Solve the system. A minus alpha I equals 0. Right? We want to solve negative 3, 3, 3, 3, negative 9, 3, 6, negative 6, 0, times x, y, z equals 0. Solving this homogeneous system is the same as saying finding the kernel of a minus alpha I. Non-zero vectors in this kernel, non-trivial solutions of this system, are the eigenvectors corresponding to alpha equals 4. Good? Okay. So let's indeed solve it. And how do we solve it? We take the coefficient matrix and do row operations until we get to the canonical one. Okay, so let's do that. So if we take the coefficient matrix, and I'm going to skip these row operations because you really know how to do it. Okay, so these are row operations. Only row operations now. Right? We're solving the system of equations. The system is preserved in the sense that we get a different system with the same solution set only if we do elementary, legitimate row operations. We can't fiddle around with columns, for example, like we do when we calculate determinants. Messes up the system. Okay? So what we get, let me tell you what we get in the end. We get 1, 0, negative 1 half, 0, 1, negative 1 half, and 0, 0, 0. This is what we get. Okay? And you can do it on your own. You know how to do this stuff. Okay? So we have two equations here, right? It's this times x, y, z equals 0, right? So x minus 1 half z equals 0. Let's write it here so we don't need a new board. So x minus z over 2 equals 0. And from this line, we get y minus z over 2 equals 0. And the third line doesn't give any information, right? So x is z over 2 and y is z over 2. And therefore, a general solution, eigenvectors corresponding to alpha equals 4 are of the form, take, okay, we can write z and then z over 2 and z over 2 for x and y. Right? That's one way of writing it. Or you can write x, x, and 2x, or whatever way you want to write it. Do you agree? Okay? And for example, you need to pick one. You have 1 degree of freedom, right? Again, the rank of the matrix is 2. Therefore, the null spaces of dimension 1, you have 1 degree of freedom. Okay? So we're going to take, so let's complete it here. Take V3. There's only going to be one linearly independent vector corresponding to alpha equals 4. And we're going to take it to be, let's take z to be 2, and then these are going to be 1s. 1, 1, and 2. Good? So the algebraic multiplicity of alpha equals 4 was 1. It appeared once as a root of the polynomial. And its geometric multiplicity is 1 again. It contributes one linearly independent vector to the basis we're trying to form. Okay? Alpha equals -2 contributed 2 guys. This contributes 1 guy. Together we have 3. How do we know that taken together they're linearly independent?
Put them on a matrix.
That would be the stubborn way to find that. What is the shorter way?
The alphas.
By definition, isn't it?
Not definition. It's a theorem that we proved. Okay? We took 2 linearly independent ones for that alpha. We take a linearly independent one for this alpha, and together they're linearly independent because of the theorem that vectors, eigenvectors, corresponding to different eigenvalues are linearly independent. That's what we proved. Okay? We proved it. We worked hard. Use it.
Yeah, but it's different because there are 2 here.
Doesn't matter. We took those 2 already to be linearly independent. Okay, so those 2 are linearly independent, and with this one, they're linearly independent as well. Okay, good? Okay, so now we have, let's summarize what we have. So for this matrix, here's the bottom line of what we did. So this was our matrix, or this was our map, and B equals V1, V2, V3, where we can say what they were precisely, if I can find it. What were they? 1, 0, -1, 0, 1, 1, 1, 0, -1, 0, 1, 1, and V3 was 1, 1, and 2. Is a basis for R3. It's a basis for the domain space of eigenvectors of A. Therefore, A is diagonalizable. Right? And what's its diagonal form? Right, the alphas across the diagonal. Okay, so let's write D, the diagonal form is -2, -2, and 4. That's the diagonal form. So this would be the matrix representation of this matrix, or of this map, arising from this matrix. This is its matrix representation with respect to this basis. And A and D are similar. Very good. A is similar to D. And what gives us the similarity? What is the P?
The 3 vectors.
As called. Very good. A is similar to D. P equals these 3 vectors as columns. So it's 1, 0, 1, 0, 1, 1, and -1, 1, 2. V1, V2, V3 as columns satisfies P inverse AP equals D. Verify. So when I say verify, I mean you know what D is, you know what P is, you know what A is, find P inverse. You still need to do that in one of the methods that we know for finding an inverse matrix, and then multiply the 3 and see that you indeed get D. That's what this verify stands for. Questions?
Yeah. When placing the alphas, when creating D, I have 3 alphas, well in this case 2. Does it matter where I put the alphas?
It doesn't matter which order you place the alphas along the diagonal, as long as it's consistent with the order of these basis element. In the sense, so you can say that this is a diagonal, that minus 2, 4, minus 2 is another diagonal representation of this t, but not with respect to this ordered basis, but rather with respect to this ordered basis. Okay? And then p would be different. You would have to change the order of the columns in p as well. Okay? So this is what's called an ordered basis. One of them is called v1, the other is called v2, and the other is called v3. And then these have to be the alphas corresponding to those v's in that order. Okay? You can reorder these, but then you would have to reorder these accordingly, and everything would still be correct. You just have to be consistent. That's the only important thing, especially when you write down what p is. Okay, if you take p in a different order than d, it's not going to work. This verification is going to fail. Good? Clear?
You said A is diagonalizable. What would make it not diagonalizable? Because the basis is free vectors because we're using...
Right. What would make it not diagonalizable is if we fail to come up with a basis of eigenvectors. And then exactly, you're leading me to our next clip. We're going to stop here and start separately. But the situation where we fail to find a basis of eigenvectors is the situation where, for example, alpha equals -2 has to contribute 2 guys in order for this to work, right? But if the null space of alpha equals -2 is only one-dimensional, it can only contribute 1 guy, one linearly independent contribution to the basis. And that's it. Then we don't have enough. We don't have enough eigenvectors. And we'll see an example. I'm not just saying it, we'll show an example.
Is it possible to get more than 3 eigenvalues for a basis of 3?
No, because the question is it possible to have, for example, for a 3x3 matrix, 4 different eigenvalues? The answer is no, because what are the eigenvalues? The eigenvalues are that's a very good question. The eigenvalues are roots of the characteristic polynomial. The characteristic polynomial for a 3x3 matrix is going to be a polynomial of degree 3. Why? Because we're subtracting alphas here and then taking a determinant. The determinant is just a bunch of products here where each row can only appear once in a product, right? In every one of those little products, you can't have more than 3 appearances of alpha. In fact, alpha to the power 3 would appear precisely when you take this times this times this. Do you agree? So the characteristic polynomial for an n by n matrix, or for a t whose domain is n-dimensional, is always of degree n. And therefore it can have at most n roots. At most. And we'll see examples when it has less than n roots. Sometimes there are not even enough alphas. Okay? For example, think of a polynomial that has no roots over R. No alphas. You can't even start. Not diagonalizable. Okay?
Over R.
Over R, exactly. If you pass to a bigger field, and this is a bit beyond the scope of this course, but then sometimes something can be non-diagonalizable over one field and okay over another field and so on. Okay, but this is a bit beyond the scope of this course. I'll mention it briefly, just as kind of ideas, but we'll do that later. Good? Okay, so really the question we're answering is not just finding the alphas and the v's, but the first step is determining will we have enough? Will we have n of them? 3 of them. Okay? Okay, so this wraps up this example, along with a bit more, I think. Do you feel that the ideas are starting to get clearer, right? Okay, so what I want to do next is collect again some ideas that we said, specifically about multiplicities, the geometric and the algebraic multiplicity, and do another example. And we'll see things a bit different. Okay, so that's coming up next.